This video is about scatter plots, regression, and correlation. Hopefully when you took algebra, you did a little bit of finding the equation or the line of best fit for a set of data. Okay, so the first thing we want to talk about is the first step that you should always take when you're trying to find a line of best fit or an equation to go with your data is to draw a scatter diagram or a scatter plot. That's a graph where the two values of both your variables are plotted along two axes, and that will give you some indication of what type of equation or regression you're looking for. Correlation measures the interdependence between the variables. So a perfect positive correlation is going to look something like this. That means that you have a really good correlation because we have a positive slope here. We have a completely straight line, and so that's a perfect positive correlation. Nothing in real life is ever perfect though. So we might be looking at something like this. Here I still have an upward trend in the data. It's still fairly straight. It just has a band of data that's not in a perfectly straight line. Still, that's a good positive correlation. No correlation is either a horizontal line or there's just data everywhere. That's no correlation. So perfect negative correlation, we'd have the same thing going on as a perfect positive, except the slope would be downhill or downward. That's what gives us a negative correlation. And again, nothing in real life is ever perfect, so a negative correlation might look something like that. Nonlinear correlation, so we can have other lines that aren't linear, might look something like this, where I have a definite curve in the data. Looks like it's related, but it has a curve in it. The correlation coefficient, that is, the linear correlation coefficient is R. That measures the strength of the linear relationship between your X and Y values in your sample. So our value of R has to always be between -1 and +1. Where I had that perfect correlation, that would be a R value of 1. And where I had not a perfect correlation, perfect positive correlation, but some correlation, that would be an R value somewhere less than 1, but not 0. And then a perfect negative correlation would have an R value of -1. And this would be less than 0, but greater than -1. Oh, and this would be greater than 0. No correlation, R is equal to 0. So the closer I am to either +1 or -1, the stronger the correlation is. So in order to determine our strength of our correlation, we have to use our table. The reason is because if I only had 2 pieces of data, then I could have a correlation of 1 because I could make a straight line between any 2 points. You'll notice that our n value starts at 3. I'd need at least 3 pieces of data in order to find a linear equation. So suppose we have a sample of 8 paired x and y values and we calculate an R value of 0.93. Is there a strong correlation? So we take the absolute value of R and we compare it. We look in the chart at n equals 8 because that's how many pieces of data we have. and our correlation coefficient must be greater than the critical value, and 0.93 is greater than 0.707. So yes, there is a strong correlation. Try that again. Suppose we have a sample of 12 paired x and y values. So we're looking at 12. All right, and so we're going to take the critical value for that, and our R value is 0.55. And we're going to take the absolute value of that and we're going to compare it to 0.576, because that's the value I'm getting from the table. The R value that we calculated is less than 0.576 if we take the absolute value, and so there is not a strong correlation, or no. Here's one for you to try. Turn this off and turn it back on when you're ready to check your answer. All right, so we have a sample size of 15, and we have a critical value. Our R value is negative 0.85, but we need the absolute value of that, and we're going to compare that to 0.514. The absolute value, even though negative 0.85 is obviously less than 0.514, the absolute value of it is greater than, so we would say yes, there is a strong correlation. So what sample size would you need to prove a strong correlation if your R value is 0.68? Why don't you try this and then check your answer? Okay, so we need the absolute value 0.68 to be greater than whatever value we find, whatever the critical value is. And I come down here, it's less than 0.707 but greater than 0.66. So greater than 0.66 would be a sample size of 9. Okay, so if we input our, now we're going to try to find a scatter plot and a regression equation. You're going to need your calculator for this. We're going to put in list 1, we're going to put the commute time, because that we believe is our independent variable, and we believe that the well-being of someone depends on their commute time. So that's going to go in list 2. And then you're going to go to stat, calculate linear regression. So after you put this data in list 1 and list 2, you go to stat, calculate linear regression. All right, so when I run that, I get an equation. Y equals 69.03 minus 0.048x. And you should have R equals negative 0.981. If you don't have that on your calculator, you need to go to your catalog. To get to the catalog, you press second 0, and up will pop like an alphabetized list of commands. You're going to find diagnostics on, sorry, it's a ways down towards the bottom, or it's a long ways in because there's a lot of commands. But after you do that, you hit enter twice, and the next time you run your regression, an R value should pop up. So now I need to know if this linear correlation is significant. It looks like it's a strong negative correlation. So if I go to my table 2 and I look up, I have 1, 2, 3, 4, 5, 6, I have 7 for my sample size. If I go to the table, I have 0.754. Which is less than the absolute value of negative 0.981. So I would say that yes, I have a significant, strong negative correlation. All right, why don't you try this one? Turn this off and turn it back on when you're ready to check your answer. Okay, you should have gotten an equation of y equals 61.37 minus 0.076x with an R value of negative 0.976. I forgot to tell you that once you turn your R value on, it'll stay on until you change your batteries or reset your calculator. So you don't have to go in and turn it on each time. So if you look, I have a sample size of 6, and I'm going to look up that value in the table. I see that it is 0.811, which is less than the absolute value of 0.976. So yes, we do have a strong linear correlation, or a significant linear correlation, and it's a negative one. Okay. So the two equations that we found are the least squares regression line. Luckily we have calculators that do that for us so that you don't need calculus. But the least squares regression line is the predicted value, the predicted y value is equal to, so this is predicted value, B1, which is your predicted slope, or your slope estimate, times x plus B0, and B0 is your predicted y-intercept, or your estimated y-intercept. And a residual is your observed value minus your predicted value. Okay, so we've already found a regression equation for this situation. It's y equals 69.03 minus 0.048x. So this is just saying, because this is a negative slope here, that as our commute goes up, our well-being goes down. So if we wanted to predict the well-being score of a person whose commute is 30 minutes, we can use our prediction equation, 69.03 minus 0.048, and for our x value we're going to put in 30, and that is going to give us a score of 69. Does that seem reasonable? Sure, why not? It's between 67.5 and 67.1 are the two values that we actually observed. And remember, this is just a predicted value. So if we want to find the residual, remember the residual is the difference between our observed values and our predicted values. So first thing we need to do is find our predicted value. So our predicted value is going to be 69.03 minus 0.048 times 50. And that gives us 71.43. Oh, let me go back to the 30-minute one. This is actually 70.47. Made a mistake in my calculation. All right, so 71.43 is the expected well-being score. What is our observed? It's 66.4. So our residual is going to be 66.4 minus 71.43. And that gives me a residual of negative 5.03. Okay, suppose a person has a 20-minute commute and scores 67.3 on the survey. Is he or she more well off than a typical individual who has a 20-minute commute? So we don't have a value for 20 minutes, so we're again going to need to calculate it by plugging it into our predicted value, and that is going to give me a score of 69.89. So that is a higher well-being score than the 67.3. So I would say that we are not more well off. In fact, we're worse off. All right, why don't you try this one on your own? Turn this off, and when you're ready to check your answer, you can turn it back on again. Okay, so our least squares regression line was y equals 61.37 minus 0.076x. So as our credit score goes up, our interest rate goes down. So score goes up, rate goes down. That's why we have a negative slope. If I wanted to predict the interest rate a person would pay if they had a credit score of 725, I would find that I would have a rate of 6.27%. So next, let's find the residual for a score of 750. Since we don't have 750, or we do have 750, so we can calculate this, the residual. I get 4.37. All right, and our observed value is 5.150. We're going to subtract our predicted value, which is 4.37, and that gives me a residual of 0.78. Pretty close. Suppose Bob has a credit score of 680 and he's offered an interest rate of 8.3. Is this a good offer? Why or why not? Well, let's use our, let's predict what we should get. So 5.15 minus, nope, that's our, sorry, wrong thing. 61.37 minus 0.076 times 680, our x value, gives me a rate of 9.69. And if I look up here, 680 is right around this value. It's higher than 675, so I should be getting a better rate than 8.6. So this is not a good offer right here. This is higher than that. Don't take it. Okay, so R squared is called the coefficient of determination, and it is R squared. It measures the proportion of total variation in your response variable, and that is explained by the least squares regression line. So our R value, because it's squared, has to be between 0 and 1, or it could be 0 or 1. So let's determine and interpret the coefficient of determination for the commute time in minutes versus the well-being score for the following printout that was done on Minitab. So here's our regression equation. Here is our R squared value. So we would say that 96.1% of the variance in well-being, it's explained by the least squares regression line. And furthermore, 3.9% of the variance, that's what's left out of 100%, is determined by other factors. Ideally, you want all of your variance to be explained by the least squares regression line. All right, let's try another one. Here is the interest rate problem. Here is our regression equation. Our R squared value is 95.2. So we would say that 95.2% of the variance in interest rate is explained by the least squares regression line. And what does that leave? 4.8% of the variance. Oh, in interest rates. This should say in interest rates, because we have to be specific when we're speaking math. Is determined by other factors. All right, why don't you try this one yourself and turn this back on when you're ready to check your answer. All right, here's our R squared value. If we wanted to interpret this, 83% of the variance in head circumference is determined by the least squares line. 17% of the variance in head circumference. Is determined by other factors. All right, that's it. Sorry it was such a long video today. We'll see you in class.